In this question, the principal stresses at a point inside a solid object are given to us. The yield strength of the material is 200 megapascal. The factor of safety calculated using Tresca theory is Nt, and the factor of safety calculated using von Mises theory is Nv. Then which one of the following relations is true? So let's find out the factor of safety for the two theories. Now we know for Tresca theory, the equation is tau max will be sigma y by 2 fs, where fs is the factor of safety, and for von Mises theory, the equation is sigma von Mises is sigma y by fs. Fs is the factor of safety. So how do we find out tau max when sigma 1, sigma 2 and sigma 3 are known? So we have tau max is maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 1 minus sigma 3 by 2. So now substituting the values, we'll get, so sigma 1 and sigma 2 are equal. So first one is 0. Sigma 2 is 100, sigma 3 is 0, so this will be 50. And sigma 1 is 100, sigma 3 is 0, so this will also be 50. So the maximum shear stress is 50 MPa. And so Nt, that is the factor of safety using Tresca theory, will be, so Fs goes to the numerator, this will be sigma y by 2 tau max. So this is going to be 200 by 2 times 50. So we get the value of Nt is 2. So I'll just write it down over here. Nt is equal to 2. The von Mises stress is given by, and so substituting the values, we will have the first term sigma 1 minus sigma 2 will be 0. The second term sigma 2 minus sigma 3 will be 100 square. Third term sigma 1 minus sigma 3 will also be 100 squared upon 2. So we have 2 times 100 square divided by 2. So 2 and 2 will get cancelled, and then sigma v will be 100 megapascal. And so Nv will be sigma y by sigma v, that will be 200 by 100, which is equal to 2. So we get Nv is also equal to 2. So the answer for this question will be option C. This question says, at a critical point in a component, the state of stress is given as sigma xx is 100 megapascal, sigma yy is 220 megapascal, and sigma xy equal to sigma yx is 80 megapascal. All the other stress components are 0. The yield strength of the material is 468 megapascal, and we have to find out the factor of safety on the basis of maximum shear stress theory. So from the state of stress, we realize that it is a plane stress condition. So the principal stresses sigma 1 and sigma 2 will be given by, so these are the usual notations. Now here sigma xx means sigma x, sigma yy means sigma y, and sigma xy equal to sigma yx means this is the shear stress tau xy. So let's substitute the values one by one. So on doing the calculations, we get sigma 1 will be 260 megapascal, sigma 2 will be 60 megapascal. And since it is plane stress, sigma 3 will be 0. So I'll note down the values on the side. Sigma 1 is 260, sigma 2 is 60, and sigma 3 is 0. Now tau max will be given by maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 1 minus sigma 3 by 2. So this will be maximum of, now sigma 1 is 260, sigma 2 is 60. So this is 200 by 2, this will be 100. Sigma 2 is 60, sigma 3 is 0, so this will be 60 by 2, 30. And sigma 1 is 260, sigma 3 is 0, so this will be 260 by 2, 130. So we have the maximum shear stress is 130 megapascal. Now by maximum shear stress theory, we have tau max is sigma y by 2 fs. So the factor of safety will be sigma y by 2 times tau max. So therefore this will be sigma y is given to us as 468 upon 2 times tau max is 130. So this on calculation gives 1.8. So the answer for this question will be 1.8. Consider the two states of stress as shown in the configurations 1 and 2 in this diagram. From the standpoint of distortion energy criterion, that is the von Mises criterion, which one of the following statements is true. And these are the options that are given to us. Now we are used to writing the von Mises criterion in terms of the principal stresses, that is sigma 1, sigma 2 and sigma 3. But in this question they are given the state of stress. So you can also remember the von Mises stress in terms of the elements of the state of stress for questions like these. It is given by, so let's mark a coordinate frame for this question. So let's say this is x direction, this is y direction and this is z direction. So calculating von Mises stress for configuration 1 we will have, so in this case sigma x is 0, this is sigma y, so we will have sigma square plus, there is no normal stress in z direction, so we will have the second term will also be sigma square, the third term will be 0. Now looking at this shear stress, this is tau yz, so we have a 6 tau square term divided by 2, which can be simplified to under root sigma square plus 3 tau square. Similarly, for configuration 2, the von Mises stress will be, so there is no normal stress in x and z direction, so the first two terms will be exactly same, sigma square plus sigma square. So this is tau xz which is given to us, so this will be plus 6 tau square by 2. So if you see, both the configurations have the same von Mises stress, so even this will be simplified to the same value, that is under root sigma square plus 3 tau square. So what we find is both the configurations have the same von Mises stress. So when they will start yielding, both of them will start yielding together. So the answer will be option C. Both will yield simultaneously. Bars of square and circular cross section with 0.5 meter length are made of a material with shear strength of 20 megapascal. The square bar cross section dimension is 4 cm by 4 cm and the cylindrical bar cross section diameter is 4 cm. The specimens are loaded as shown in the figure. So these are the loadings. Which of the specimens will fail due to the applied load as per the maximum shear stress theory? So let's find out maximum shear stress for each of them. First one is a tensile load. So this is a case of a simple tension. So it will be a uniaxial state of stress. So whatever tensile stress that we will be finding out will be sigma 1 and sigma 2 and sigma 3 will be 0. So sigma 1 will be the load upon area, which is 80 kilonewton. So that will be 80 into 10 raised to 3 upon, this is a square bar which is having a cross section 4 cm by 4 cm. So this will be 40 mm by 40 mm. And so this is equal to 50 megapascal. Sigma 2 and sigma 3 are 0. So tau max, which is maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2 and sigma 1 minus sigma 3 by 2. In this case, it will be equal to 25 megapascal. So we have tau max for the first case, that is of tensile loading, is 25 megapascal. So if you look at the question again, the question says the shear strength of the material is 20 megapascal and we have to find out which of the specimens will fail as per the maximum shear stress theory. So the options are tensile and compressive load, torsional load, bending load and none of the specimens. Now what we have found out is when it is a tensile loading case, the maximum shear stress is 25 megapascal, which is more than the shear strength of the material. So clearly this tensile load specimen will fail as per the shear stress theory. So looking at the options, we do have one of them which will be failing. So none of these is not the answer. And there is tensile load specimen present only in option A. So the answer will be option A. So this was asked for 2 marks, but then when we look at the options simultaneously while solving the question, we figure out that the answer is option A and we do not have to do calculations for all the loadings. However, you can still go on to verify that the compressive load specimen will also fail, because in this case what is happening is just the nature of load is changing. So instead of a tensile stress of 50 megapascal, we will have a compressive stress of 50 megapascal. But then the maximum shear stress will still come out to be 25 MPa. So the compressive loading specimen will also fail as per the maximum shear stress theory. And then you can go on to verify that the torsional load and bending load specimens will not fail. Their maximum shear stress will turn out to be less than 20 megapascal. For this torsional load specimen, we get the maximum shear stress, which is the torsional shear stress. It turns out to be 16 megapascal. And for this bending load specimen, we get the maximum bending stress is 30 megapascal, which again is like a uniaxial stress. So the maximum shear stress in that case turns out to be 15 megapascal. So options B and C do get eliminated and option A is correct, which we actually figured out long time ago. So during a GATE exam, just be alert and just check the options in such type of questions, because otherwise it will take a long time if you first calculate the maximum shear stress for all the cases and then come to options. Alright, so you can save time in such questions. The homogeneous state of stress for a metal part undergoing plastic deformation is given by this tensor. So this is a stress tensor. Here the stress component values are in megapascal. Using von Mises yield criterion, the value of estimated shear yield strength in megapascal is. So what does the question say? That the metal part has started undergoing plastic deformation. So the material has started yielding. So whatever von Mises stress we get for this state of stress, it will be equal to the yield strength of the material. That is what you need to understand. So once again, we are not given the principal stresses, that is sigma 1, sigma 2, sigma 3. Instead, we are given a stress tensor. So we'll use the von Mises equation, which is in terms of the elements of the state of stress, which is given by. So substituting the values, we will have sigma x is 10, sigma y is 20. So this is minus 10 the whole square plus sigma y is 20, sigma z is minus 10. So this will be 30 squared plus sigma x is 10, sigma z is minus 10. So this will be 20 squared plus 6 times tau xy is 5, tau yz and tau zx are 0. So this comes out to 27.84 MPa. So since the metal part is undergoing plastic deformation, we can say that the yield strength of the material will be 27.84 MPa. But the question is asking what is the shear yield strength of the material. So we know by von Mises criterion the shear yield strength is nothing but sigma y by root 3, which comes out to 16.07 megapascal. So therefore the shear yield strength is 16.07 megapascal and the answer will be option B. Now as an alternate method to this question, what you can do is first find out what are the principal stresses. The principal stresses are nothing but the eigenvalues of a stress tensor. So you can find out the eigenvalues of the stress tensor, and then once you know the principal stresses, you can find out the von Mises stresses using the equation in terms of principal stresses.